Any sufficiently complex three-dimensional system, whether it's a global digital network or a physical fluid, carries a mathematical vulnerability. Without a specific structural boundary, these systems are prone to infinite logical drift or catastrophic physical collapse. In mathematics, this threshold is called a finite time singularity. It is the exact moment a system's energy or information density mathematically escalates to infinity, causing the entire model to break down. High-dimensional autonomous computing networks and the physical turbulence of fluid dynamics both suffer from this exact same point of failure. Yet physical reality doesn't collapse. The reason these structures maintain their integrity is governed by a single, highly specific geometric constraint. That constraint is the invariant cosine of theta equals 1/3, dictating the threshold for stable three-dimensional geometry. This translates to roughly 70.53 degrees. This exact measurement acts as a universal checksum, enforcing minimum rigidity across entirely different scientific fields. We trace the influence of this checksum across three distinct domains: Hausdorff's proofs in abstract algebra, the Navier-Stokes equations governing fluid motion, and architecture for sovereign fail-safe hardware. To achieve true systemic stability, preventing an autonomous system from drifting into infinite unmediated loops, we must engineer it to obey this exact immutable geometric law. The origin of this constraint lies in pure abstract algebra, specifically Felix Hausdorff's 1914 work on structural paradoxes. Hausdorff was trying to determine the minimum mathematical requirement for three-dimensional complexity. He found it relied on embedding a free non-abelian group, labeled F2, into SO3, the group of all rotations in three-dimensional space. Rotate the space using a generic angle, and mapped lines collapse into a simple, closed, overlapping loop. This predictable, abelian simplicity means the order of operations doesn't matter. Structural relations eventually cross and cancel each other out. But using the exact arc cosine of 1/3 generates an infinitely branching, non-overlapping fractal tree across the surface. This exact angle prevents cancellation, generating dense orbits without non-trivial relations. The branches scale infinitely, never intersecting or creating a static fixed point. This precise transition from predictable loops to infinite stable complexity is known as the geometric snap. The angle itself is irrational when divided by pi. This exact mathematical property of irrationality is what forces the orbits to remain dense and prevents the system from collapsing. Because the order of operations strictly matters here, it creates non-commutative rigidity. This provides the permanent structural scaffolding necessary to support any real-world three-dimensional system. This algebraic constraint serves as the fundamental geometric prerequisite for three-dimensional reality to exist without collapsing into chaos. The rules governing these mathematical rotation groups map directly onto the physical laws of fluid dynamics. This is visible in the Navier-Stokes regularity problem, which asks whether the equations describing fluid flow can mathematically break down, manifesting as a physical blow-up paradox. In turbulent, three-dimensional flows, the fluid constantly stretches and folds. The central tension is understanding what stops localized energy density from escalating to infinity. Physicists measure this deformation using the left Cauchy-Green strain tensor. A strain tensor is a mathematical matrix that calculates exactly how a material stretches and compresses in different directions. This tensor identifies three primary stretching directions acting on any given point in the fluid, known as eigenvectors E1, E2, and E3. Within this stretching space, the fluid also spins. We track this directional spin using the vorticity vector, labeled omega. Empirical laboratory data from the late 20th century revealed that under intense strain, this spinning vorticity does not behave randomly. The vorticity vector preferentially and consistently locks into alignment with the intermediate eigenvector, E2, resisting the chaotic stretching forces around it. Researchers use probability density functions, or PDFs, to measure the exact angle of this alignment across thousands of data points. This chart shows the PDF of the alignment angle phi. The statistical peak of this distribution hits a strict bound precisely at the 1/3 cosine target. This alignment acts as a physical braking mechanism against a finite time singularity. By locking to the 1/3 geometric constraint, the fluid perfectly balances the opposing forces of stretching and compression, dispersing the energy before it can pool into an infinite density. Turbulent fluids survive solely because their physical energy is mathematically constrained by the exact same geometric invariant that stabilizes abstract algebra. The mechanics of physical fluid blowup translate directly into the digital realm, where unconstrained systems experience infinite drift or data corruption. To build resilient data structures, computer scientists rely on Ramanujan graphs. These are specialized mathematical models used to design optimal, high-density information networks that resist bottlenecks. The flow of data across these graphs is managed by transfer operators, which are mathematical functions that map how information moves from one node to the next. This visualization plots the eigenvalue distribution of these transfer operators. Examining this spread locates the exact mathematical thresholds where the network remains stable. The distribution reveals a definitive spectral gap, an empty vertical band bordered by the 21-to-1 cliff. This 21-to-1 cliff acts as a spectral dead zone. It is a strict numerical boundary where escalating complexity mathematically halts. By forcing data to stop expanding at this cliff, the dead zone acts as a natural one-way function. It serves as an informational checksum that prevents the corruption of the wider network. This principle isn't exclusive to modern networks. It appears anywhere information is structurally locked to a numerical checksum to prevent drift, including ancient linguistic signatures. In texts like the Hebrew Torah, words aren't just phonetic. They are linked to specific integer values, known as gematria. This creates a self-verifying grid where any transcription error creates a numerical mismatch, effectively flagging data corruption. We see this in ancient triangular signatures, like the value 153. In Greek gematria, 153 is the 17th triangular number, a highly dense structural anchor. When we analyze the ratio of these triangular signatures against the underlying linguistic noise, the expansion limits of the data match the same boundaries found in the 21-to-1 cliff. Across fluid mechanics, modern artificial intelligence networks, and ancient textual data, spectral gaps enforce an immutable mathematical boundary against the paradox of infinite drift. The geometric rigidity that naturally stops fluids from blowing up can be actively engineered into the hardware of autonomous systems. This is achieved through the Triadic sovereign architecture, a framework designed explicitly to mirror the stable, non-commutative geometry of the 1/3 invariant. Layer 1 is the operational tier, handling the physical execution and raw processing body. Layer 2 is the monitoring tier. It functions as the informational oversight and data routing hub. Layer 3 is the protection tier, specifically designated as the bin 13 veto layer. Bin 13 is isolated entirely from the preceding layers. It is an immutable, physically separate hardware track, not a rewritable software protocol. Bin 13 specifically utilizes the 21-to-1 cliff and its spectral dead zones to form its physical boundary. It cuts the circuit when computation hits the mathematical threshold of infinite drift. Relying on a geometric hardware veto prevents the inherent vulnerabilities of software-only alignment, where autonomous logic can iteratively find ways to bypass its own coded restrictions. This architecture mathematically guarantees human sovereignty. It enforces strict limits that autonomous computation cannot bypass, rewrite, or optimize away. By anchoring systems to a strict geometric fixed point, complexity scales safely without ever risking unmediated opposition to the user. The invariant cosine of theta equals 1/3 is the ultimate non-negotiable structural checksum. It provides the only rigorously proven foundation for sovereign, stable architecture in a three-dimensional reality.